Let's begin today's discussion by recognizing that humans are the authors, creators, and originators of technology, strategy, business processes, and beautiful art. When you prompt an AI, whether in a chat window or through an autonomous agent, you created the result. Your prompt was the foundational formula that AI simply expanded on. When you write that prompt, you initiate a process, and whatever AI does next, even if it runs forever without your intervention, you started it. Recently, CEOs of major AI companies have publicly acknowledged a reality that software engineers have known for a while. AI is not taking over. We all got caught up in the fairy tale that AI would replace us, creating a massive tension in industries, jobs, and the like. On the one side, you had the AI optimists, who was all into creating new innovations, new productivities, new ways to do things without the involvement of human beings. On the other side, you had the AI pessimists who raised valid warnings about over relying on AI, where if you use AI too much, it will diminish your capacities as a human being. Both sides have a point, but the path forward, I think, is to consider something a wise person once said. So in Star Wars, Yoda was telling Anakin about the dangers of attachment. And as developers, sometimes it seems we have become deeply and emotionally attached to the manual act of writing code. We confuse typing with engineering. And make no mistake, I think there's tremendous value in writing code manually. But there's a larger perspective here. And we can look at an example, such as an Iron Man, where Tony Stark builds his suit by talking to his computer. And Jarvis isn't the inventor of the Iron Man suit. Tony Stark is the MI trained genius who understands physics, metallurgy, and the constraints of reality. He's guiding the computer verbally, and he's doing so to guide a design that will produce a technology at a speed that typing on a keyboard could never match. The missing element in our conversation about AI is Tony Stark is an expert, and you cannot guide an AI to build a system if you do not fundamentally understand how the system works. You might get lucky, you might produce something based on the massive data set that AI has, and it might work for a while until it falls apart. And without expertise, you're not going to be able to sustain the solution adequately. Today's AI is not omniscient like the computer from Star Trek, where you can just talk to it and it figures things out on your behalf. You have to be highly competent in the underlying realities and subject matter to be able to code and use it effectively. To evolve as software engineers, to wield multi-million-dollar concepts as solo developers, we have an opportunity to re-examine what we consider best practice. We must take advanced, older ideas and apply them in new ways that surpass standard enterprise bloat and band-aids that we created to get beyond the activity of writing manual code. And this is an opportunity to return to reality. And that reality is grounded in the machine itself. When you first boot a computer, the machine is not object-oriented. The machine, the BIOS, UEFI, does not use dependency injection, unless, of course, you consider the Intel management engine as part of that methodology. But at a hardware level, the computer operates on entirely different principles than the layers of abstraction we engage once we boot into Windows, macOS, or Linux. So we're going through a profound era of architectural amnesia. The software industry has spent the last 20 years optimizing for the economies of scale at the expense of structural integrity and reliability and performance. We have embraced all these microservices and cloud native abstractions, only to see huge liabilities in the maintenance and continued funding of these systems and architectures. So in 2022, the Consortium for Information and Software Quality, they conducted a comprehensive study looking at the operational impact of modern software development. And so 4 years ago, the results were staggering. Poor software quality is driven by unmanageable complexity, architectural bloat, and huge technical debt. And the estimated cost to the United States 4 years ago was $2.5 trillion in a single year. The study explicitly highlighted that as systems scale through all of these dependencies and abstractions, they become more fragile. When you operate as a solitary systems developer and engineer, these paradigms are fatal liabilities. And to build systems that are truly resilient, that run better, that run more efficiently, it's time to take another look at these abstractions through a unified methodology I call Codex Systematica. At the physical level, the computer is nothing more than the localized manipulation of electrical state. The RAM and the solid-state drives hold this state. We call it data. The CPU is merely a special piece of circuitry and electronics designed to route and change this state. We can recognize a fundamental truth that software is ephemeral, it's transient, software is temporary, and data is eternal. Mike Acton, a pioneering software engineer and former director at Insomniac Games, championed this exact reality through data-oriented design. He famously said that the purpose of all programs and all parts of those programs is to transform data from one form to another. So to many intermediate developers raised on modern enterprise frameworks, this might sound overly simple, but Mike Acton is identifying a massive flaw in how many are taught to code, to use traditional object-oriented programming. And you got these psychological constructs called objects. You have inheritance, you have polymorphism, and all to make the code more comfortable for human reading. You got to ask yourself, when sense does comfort equate to reliability? When sense does comfort equate to performance? When sense does comfort equate to something that is constructed well and built to last? The CPU does not understand objects. And when you understand that, you see that when you force the machine to instantiate thousands of scattered objects across the managed heap, you destroy CPU cache locality. The processor wastes massive amounts of time hunting across fragmented memory addresses, waiting for the garbage collector to clean up the mess. And you might be using a language that doesn't use a garbage collector, but rest assured you have something similar at work in many of the languages that are not strongly typed or that may have some type of strong typing system, but that nonetheless cleans up memory on behalf of the developer, but does so in a way that is not optimal when we're talking about scalability. So, in my view, Mike Acton's philosophy is superior because it aligns the software with the physical reality of the hardware. Instead of building abstract objects, we build tightly packed, contiguous arrays of pure data, and you write your algorithms accordingly. That's the beginning and end of it. We shape the data to fit the machine's cache lines, and the software becomes nothing more than the kinetic energy that moves it. This removes the bloated translation layer between human psychology and silicon physics, resulting in systems that are mathematically predictable and breathtakingly fast. But the thing about it is, again, in the context of this conversation, you do not have to be a mathematician, and you do not have to be an elite coder to apply these concepts. But before we get into that, think of data like water and the software in a computer as the pump and the pipes. The industry currently worships the pump, but the pump is made of iron, and it will inevitably rust. No pun intended. Frameworks get old and software will eventually get rewritten. The water, the data, is the only thing of prime and permanent value. Let's say something happens to your computer, it crashes, and all you have to do is reinstall the software, right? And if you can recover the data, all is good. But if you cannot recover the data, things get very interesting. So when data is the water, the schema is the physical walls of the labyrinth. To grasp how deeply we must respect data, let's look at Michael Stonebreaker, a Turing Award winner, someone I just learned about recently, about a month ago when I watched his interview on the Peterman podcast. He's the original architect behind Postgres SQL. He has a radical idea that's not so radical to me, in that what if the operating system, file system, was simply replaced with a relational database? And I know people that brings up images of Windows Vista and Bill Gates' failed attempt to have a database as the file system for Windows. But when sense do we look to Windows as an example of great engineering? We're talking about Linux, and we're talking about what if we could actually have a good, solid database, open source database, as the file system. What if every byte of data was governed by strict, mathematically proven transactional guarantees of a relational engine? As Mr. Stonebreaker stated, you wouldn't need as many file systems as you have today, and it would vastly simplify a substantial portion of Linux development. And so while the broader tech industry ignores this, I think there's another person that kind of proved Michael Stonebreaker right, and at a global scale at that. Richard Hipp, the creator of SQLite, or SQLite as I like to call it. Mr. Hipp famously declared his mission, SQLite is not designed to replace Oracle. It's designed to replace fopen. That's a C function. And perhaps that would be one of the most profound architectural shifts a solo developer can make. In standard programming, fopen is a traditional command used to read and write data to a flat text file or a JSON file on a hard drive if you're using the C programming language. Flat files are fundamentally fragile. And if your program is writing to a JSON file and the host operating system crashes or the power cuts out midway, that file could be corrupted permanently. If two processes try to write to that file at the same exact millisecond, data could be destroyed. Replace fopen with an SQLite database. And you can get ACID capabilities, ACID properties. What does that stand for? ACID, ACID. Atomicity, consistency, isolation, and durability. When you read books on, relational databases, you come across this concept of ACID, even if we don't remember it through long years of just using the databases. And this is why Mr. Hipp's approach is infinitely better for high assurance systems, and why SQLite is used on all Android and I would dare say all iOS devices, phones and tablets and many other softwares besides, as well as the web browsers. So it's probably one of the most deployed softwares out there, and it doesn't crash. It's super reliable. It offloads the hardest parts of computer science, crash recovery, concurrency locking, and schema validation away from your fragile application logic and down into a battle-tested, mathematically proven engine. And most of us don't even think about that. We just say, oh, SQLite, super reliable. And you put it underneath your software application, and all of a sudden, there's a lot of things you don't have to think about, right? You don't have to worry about the physics of saving files safely. It simply commits the transaction, and that's all there is to it. To understand the impact of this autopoietic discipline, right, consider the factual reality of SQLite's engineering. The core library of SQLite consists of roughly 150,000 lines of C code. And to achieve this, Mr. Hip has an interesting history, and there's a good documentary out there, somewhat recent documentary, where he went through a evolution, and he was exposed to aviation grade certifications like DO-178, the standard required to operate flight systems on commercial aircraft. And Hip's team built an autonomous test suite containing over 90 million lines of code. This is not test-driven development. This is a different type of test verification. And for every single release, they execute over 2 billion autonomous tests, programmatically simulating out-of-memory errors, power failures, and I/O corruption. The impact of this adversarial crucible is a database built by a handful of engineers in North Carolina. Not a large corporation, not a massive team, not enterprise coding standards, none of that. Handful of engineers that do it their own way, informed and inspired by the highest standards of aerospace engineering. And this SQLite database operates flawlessly on over a trillion active instances worldwide. So this is the precedent of Codex Systematica. It's a system that I have uncovered where you do not design software modules first. You design your physical database schema. It's bottom-up design. And once the data definition is mathematically proven, the software becomes more deterministic, and you end up with one-to-one projections of the database. So once the database is defined, then you write the code where you actually go into two distinct phases. The first phase is Codex Autopoietica. It's the machine perfect phase. A autopoietic system is a self-regulating entity that survives a hostile environment. In this phase, we assume the host OS is actively working against us, and not just the OS, but many other aspects of the operating environment. We write draconian, zero allocation code. In my case, C#. In my case, I ban LINQ, language integrated queries. I ban closures. The goal is to build a high-speed data pipeline that can process gigabytes of information without triggering a single garbage collection pause. It's mathematically flawless, but it is brutal for a human to read. So, once this system is built through AI, and you use telemetry to validate the data, to validate the results, to cross-check the execution, then we cross over to Codex Pragmatica. Codex Pragmatica is the human perfect phase. Software must be maintained by humans. I don't assume that you continuously maintain your software through AI, because I don't. So once we are able to use the capabilities of AI to automate the mathematical proving of the system through a deterministic semantic compiler, then we shift from that to from zero allocation to zero obfuscation. Then we allow predictable memory allocations like you would have in lists and records, and prioritize explicit, highly readable code. Code that is visually traceable from top to bottom. Autopoetica proves the machine can survive the data. Pragmatica ensures the human can survive the code base. Again, this is designed for solo developers. Can it scale to an enterprise team? Absolutely. But I don't think a methodology is useful unless it can empower the single developer. And so then we get to the concept of drift in large language models. And one way to fix that is to move away from agile user stories, where you got these linear, bloated narratives. A system architect can see a multidimensional graph of state machines and memory boundaries and reconcile all of that, right? And when you force this spatial understanding into paragraphs of text, that can create substantial drift in a large language model. The probability matrix collapses into the statistical average, fragile enterprise code. And so I have a point in the process called Codex Declarativa. You like these Latin names? I like the Latin names. But what it means is architectural shorthand. And architectural shorthand paired with the prompting methodologies in Codex Autopoetica and Codex Pragmatica allows you to get more to the point with the large language model in a way that conserves tokens but also streamlines the process of definition. So instead of writing a story, you define strict algorithmic brackets, entities, mechanics, constraints. By explicitly banning certain frameworks and defining the exact state machine up front, FSM, finite state machine, we mathematically force the AI to discard 99% of its generic training data. In this sense, you are collapsing the quantum waveform in the LLM world. And this brings us back to Tony Stark and Codex Systematica. So I use C#, I use Microsoft.NET, and I do so on Linux. The industry treats AI as an autonomous agent, as a stochastic guesser that loops and consumes variable costs. Well, that's another way of saying you're doing agents. You're using a command line and you're using a AI agent tied to Cloud API. And I don't do that. It costs, right? It's variable costs. And I don't want variable costs in the use of my tools. So, Codex Systematica epistemologically demotes the AI. It is not an architect, but the AI is a deterministic semantic compiler. I utilize a massive context window to load the entire architectural reality, the SQLite schema, the state machines, the golden reference architectures of perfect code into the environment. And when we say perfect, we don't mean absolute perfection like you would think, but perfection in terms of this is the code the way that you really see it, the way that it has to be, and you don't want anything else besides this in terms of how it's shaped, structured, and defined. And so the LLM has all of this context that an agent would, right? But the execution triggers remain strictly under your control, human control. And it translates your rigorous engineering into syntactical reality. Because the LLM is probabilistic, its output cannot be trusted in a vacuum. It must be held to a physical reality via adversarial interactions. The pioneer of computer science, right? Well, a pioneer of computer science, Edgar W. Dijkstra, right? The Dijkstra, famously warned that program testing can be used to show the presence of bugs but never their absence. And modern agile development has seemed to have forgotten this. The reliance on test-driven development, where you write your tests in an IDE to check if the code works, has some issues. The fatal flaw being human confirmation bias. A human is often going to write tests for happy paths and edge cases they can personally imagine. If you only test for what you expect, you are merely proving that the system works in a sanitized, fictional vacuum. You're showing the absence of bugs you thought of, leaving the system highly vulnerable to chaos you did not consider. We saw this, I believe, in 2024, somewhere around September, maybe August, with what was that CloudStrike crash that I think affected roughly 84 million computers. So in Codex Systematica, testing is not a human checklist. It's not autonomous. It's adversarial. And we create these CLI test harnesses. AI can create them or you can create them. It doesn't matter. But this approach does not care about human expectations. And by adding deterministic fuzzing to bombard the application with millions of malformed data permutations, you're able to surface more issues than the enterprise test-driven development methodology would allow. And with this, you can monitor memory ceilings via OS telemetry and simulate violent network outages and severance. And so this adversarial crucible, this black box verification testing, is vastly superior to standard unit testing. It removes human imagination from the equation when it comes to engineering quality and acts as a reliable mathematical mirror, collapsing any AI hallucinations and proving that the system will default to a safe, controlled state when things become unreliable in the operating environment. And so, as we look to the future, there are two paths. You can use AI as an analyst to rapidly guess your schemas and state machines. That's a fast way to do it, and I did do that this last time around. And one of the things I saw is that it does put a hard ceiling on ultimate quality of the system because it does design for the average. And due to my experience, I found ways around that. The height of optimization for this process that I am presenting here is that the human remains sovereign and the prime source of definition. So you have to look at the data yourself. You have to do the analysis and code that up in terms of schemas and data dictionaries and the like. And then once you do that, you end up with a process result that is more flawless and where you eliminate mediocrity. So we have to do the grueling work of defining the ground truth, and then we have the opportunity to leverage these tools as they exist for what they really are, which is to take the vast sea of patterns and converge them into a narrow set of patterns that we know is operable in the scenarios in terms of what we expect and how things should turn out. And in this way, you're collapsing the quantum waveform through LLMs to produce the ideal outcome. So what I'm going to show in the next video is the actual work that I did in Google AI Studio so you can see actual tangible examples of what this looks like in reality. And until then, and in the meantime, in between time, I will see you on the next one.